Today we want to talk about trigonometric identities and how we as trig students need to think about trigonometric identities. Here's the important thing to know. Trig functions, sine, cosine, tangent, secant, cosecant, cotangent, and the others, they're all related in a lot of different ways. Trig functions are related in many different ways. It's less important that we remember all the different ways that the trig functions are related, and more important to remember that they are related. So what that means is that it's not critical to memorize all of your trig identities. We don't get a lot of mileage out of memorizing all of our trig identities. We get way more mileage about remembering the existence of trig identities. And we'll demonstrate that in a minute. So trig functions are related in many different ways. The most important thing to remember is that they are related. We break the trig identities into so we're going to divide these relationships, how the way that they're related, into groups of identities. Trig functions are related in many different ways. We divide these relationships, we categorize them into groups of identities. Identity is just an equation that's always true. An identity is just an equation that is always true. Always true, asterisk, always true insofar as that it's true for all the values for which it is defined. Don't at me in the comments. What's important to remember is these different groups or categories that they exist, not to remember the specific identities. It's way more important to remember what groups we have rather than try to memorize all of the identities. Do not try to memorize all the identities. There are some that are more important than others. There are some that you should carry with you always. Too many E's and remember. We should remember our foundational identities, the categories of ratio identities, reciprocal identities, and Pythagorean identities. Ratio is important because tangent is sine over cosine. That's an important relationship between tangent, sine, and cosine. Secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tangent. That's kind of how we define our secant and cosecant functions. In particular, secant is the one that we really care about most. And our 9 Pythagorean identities, all variations of cosine squared plus sine squared is equal to 1. These ones we should always have at the ready. There are many more categories. And if you were wondering who I was just texting, I was texting Google to find out the details of the sum and difference identities on which a lot of these are based. So what's more important about trig identities is you remember that trig identities are all related in many different ways. And then remember the different categories in which they are related so that you could just look them up when you need them, like I just did. At the first level, we have sum and difference identities. This is when we have a trig function applied to a sum or a difference. We were doing capitals for our angles. So things like this sum identity for sine, a difference identity for sine, a sum identity for cosine, and a difference identity for cosine. From these, we will build other identities. We just want to see the structure. Okay, so of what we write down here, there's got a lot of ways to remember how these are set up. I don't know which way is going to work best for you. I do know, oops, that's not the one I want. I do know what works best for me. In particular, if you just look at images, this is the time I'm going to get an interesting thing, and just grab sum and difference identities. This is the best way to remember them because we carry phones in our pocket for a reason. So sine of a plus b, notice it's combinations of sine alpha and cosine of beta, and cosine of a plus b is cosine alpha and cosine of beta. Notice that sine has a mix, sine cosine, cosine sine. Cosine has the same, cosine cosine, sine sine. So that's one way we can remember these. If some crazy person asks you to memorize them, which I'm definitely not asking you to do. I don't even want you to try to memorize them. Sine is the one that's kind of like mixed. We have a sine alpha times cosine beta plus cosine alpha times sine beta. The other reason it's really important that we look at this is that when we see sine of alpha plus beta, it gives us this visual structure of a sum in parentheses, and we will want to distribute. And clearly we cannot just distribute because it's not sine times the sum alpha plus beta, it's sine of alpha plus beta. It's not a multiplication, it's multiplication that distributes over addition. So first thing that we notice is that sine is the mixed one and cosine has the same. Cosine, cosine, sine, sine. So that might be the first thing that we notice. Sine is sine, cosine, cosine, sine, kind of mixing it up. And cosine is cosine, cosine, sine, sine. Also notice that sine of alpha plus beta has a plus, but sine of alpha minus beta is the same thing, but with a minus. So it's sine alpha cosine beta minus cosine alpha sine beta. But cosine of alpha plus beta has a minus, and cosine of alpha minus beta has a plus. This is one of those situations where if you remember one, you kind of get the other three for free. If you remember the things that you have to look for in the pattern. Also notice we've got these two for tangents. And they have that similar, they have a different structure than the sines and cosine ones. We also note that tangent and is related to sine and cosine. Tangent is sine over cosine. So if we forget the tangent one, we can build it from the sines and cosines. The important part of this whole block of stuff, this wall of text that I just assaulted you with, is that this category is called sum and difference identities. This is our first level of trig identities beyond our foundational ones. Any questions? It was like, oh, no, you told us we didn't have to memorize these. You also showed us that they are available on the internet. So I'm not even writing them down, although some of you are writing. We want to see how these are related. So the next level up from this is double angle identities. This is the category of identity, a double angle identity. The reason I put this as second level, even though this is the one that I remember more often, the reason that I remember it more often is because I taught Calc 2 for a very, very long time. And one of these is kind of important in Calc 2. Important is kind of overstating it. Comes up a lot. The reason that this is the next level after sum and difference identities, a double angle identity is just the sum and difference identities where alpha and beta are the same. Or sum identities, it's the sum identity. A double angle identity is just where alpha is equal to beta. So instead of alpha plus beta, we have alpha plus alpha, or 2 alpha. That's the double angle in the double angle identity. And so I'll have sine of alpha times the cosine of alpha plus the cosine of alpha times the sine of alpha. It's just our sum identity for sine, but where alpha and beta are the same. Now notice that sine alpha, cosine alpha, and cosine alpha, sine alpha are the same. So what we have is 2 sine alpha, cosine alpha. And then we just do the same thing for cosine. This one plays out a little bit different because now our first term is cosine alpha times cosine alpha. So we'll write that as cosine squared alpha. And sine alpha times sine alpha is sine squared alpha. The double angle identities came directly from our sum identities. Now notice that the cosines of 2 alpha has cosine squared and sine squared. And we know that sine squared plus cosine squared is equal to 1 from our Pythagorean identity. So if I replace the sine squared with 1 minus cosine squared, I can say cosine of 2 alpha is also cosine squared alpha minus 1 minus cosine squared. So I have cosine squared minus 1 plus cosine squared. So I get cosine of 2 alpha is cosine squared alpha minus 1. So we have this variation of the double angle identity for cosine. But wait, there's more. I know you're like, oh no, please no. It's like, oh no, there is more. If you call now, you can get one bonus double angle identity for cosine. So I'm not calling now. It's like, well, yeah, you are. Because I'll also throw in these absorbent towels. I don't think they sell stuff like that on TV anymore, do they? I think it's just influencers. Like, oh, guys, I've just found the most important thing that I've ever discovered in my life. This company has sent me some super absorbent towels. Here's how they work. So this cosine, here I use sine squared as 1 minus cosine squared, but it's also true that cosine squared alpha is 1 minus sine squared alpha. So I can write cosine of 2 alpha as, I can replace the cosine squared with 1 minus sine squared. And then finish with minus sine squared. So now I have this other variation of the cosine, the double angle identity for cosine. Cosine of 2 alpha is 1 minus 2. I forgot the 2. Sine squared alpha. So we've got all these variations on all these variations for the double angle identity for cosine. The problem with these, introducing these at this point, is that we don't really have a strong motivation for why one is better than the other. And I hate to say it, but it becomes important when we're composing functions. Cosine squared is decidedly inconvenient, but cosine of 2 alpha is super convenient. So if we need a reason, sometimes it's messy to have the square of a trig function. If we think about, if we just think about functions in general, if we want to invert a square, we have to do this plus or minus thing. So we have the square function, which is not invertible. The square operation that's not invertible. We also have a cosine and sine. Neither of those functions are invertible unless we restrict our domains and ranges. However, cosine of 2 alpha, cosine is invertible, but 2 times is not. Multiplying by 2 is invertible. It's more convenient to have cosine of 2 alpha in some scenarios than it is to have cosine squared. The next level would be half angle identities, which is just taking these 2 double angle identities and turning them around, solving for the alpha parts. So that's a new category of identity, a half angle identity. You're just gonna grab those two double angle identities for cosine and invert them. Solve for the cosine of alpha, because alpha is half of 2 alpha. Half angle identities. Always my favorite method for remembering my half angle identities. Oh, you did. You didn't give me. Siri, you failed me. Half angle identities. Best way to remember them. Any questions? Using these trig identities at this point in your career becomes very contrived, and we don't really have time for that. If you're wondering if I deliberately set things up so we wouldn't have time for that, that's a terrible accusation, but I would drag my feet so I wouldn't have to do these terribly contrived problems. The most important thing is that you remember that if you get stuck on a problem in your future and trig functions are involved, it's probably there's a trig identity that will get you out of it. All right, I have to cut class early today. That's going to do it for today. I will see you all on Thursday. Everybody have a good day, and thanks for playing.